Hello everyone, welcome to Neso Academy. In the last lecture, we learned about the behavioral modeling. Now, behavioral modeling describes what the circuit does, meaning, behavioral modeling describes the behavior of the circuit, which includes input output behavior. Now, in this lecture, we are going to learn about the second modeling style, structural modeling. Unlike behavioral modeling, which describes the behavior or functionality of the circuit, structural modeling describes the internal circuit structure or internal components and their interconnections. In simple words, structural modeling describes how the circuit is physically connected. So, in this lecture, we will understand what is structural modeling. Now, to know more about the difference between behavioral modeling and structural modeling, think about a computer. How we can describe a computer? We can describe a computer by using two ways. First, behavioral view. Now, behavioral modeling is similar to behavioral view. Behavioral view describes a computer as a device which can perform calculations and stores data. So, behavioral modeling is similar to behavioral view, where it describes the behavior of a computer. Now, second way to describe a computer is by using structural view. Now, structural modeling is similar to structural view. Structural view will describe a computer as a device which contains RAM, memory, motherboard, and their interconnections. And using these, it can perform calculations and stores data. So, structural modeling is similar to structural view, where it is describing the internal circuit structure. So, in digital electronics, behavioral modeling describes the behavior of the circuit, and structural modeling describes the internal circuit structure, similar to a circuit diagram. Now, let us understand the structural modeling using the half adder. I have already explained you what is the half adder. Half adder is a circuit which performs addition of two single bits, let's say A and B, and generates two outputs, sum and carry. Now, in behavioral modeling, we described the behavior of this half adder, where we described the relationship between inputs and outputs using the truth table. Now, to understand structural modeling, carefully look at the structure of this half adder. Here we have two logic gates, XOR gate and AND gate, where these two gates are connected with these two inputs A and B, and the XOR gate is connected with the output sum, and the AND gate is connected with the output carry. In structural modeling, we need to define these two logic gates separately and then connect them together to create the half adder. So, in structural modeling, we need to write the VHDL code for these two logic gates separately and then connect them together to create the structure of the half adder. So here, I am writing the VHDL code for this AND gate. Now, we have already seen this VHDL code for AND gate in previous lectures. This VHDL code consists of three blocks: library, entity, and architecture. In library, we will declare IEEE library and standard logic package. Then we have our second block, entity. Inside the entity, we will define the input-output ports. And here I am naming this entity as AND_gate because we are writing the VHDL code for this AND gate. And here we have two input AND gate. So we are declaring two inputs, let's say X and Y, and one output Z. And both of these inputs and output are of standard logic data type. After port declaration, we can end this entity using the keyword end and the name of the entity and underscore gate. After entity, what comes next? The important block, architecture. So here I am writing the architecture using the keyword architecture, and I am naming this architecture as data flow, because here we are writing the data flow architecture. Now don't worry, we will understand about this data flow architecture in the next lecture of data flow modeling. Now just focus on the code that I have written here. Architecture data flow of entity and underscore gate is. After the keyword begin, we will write the Boolean expression. As in data flow modeling, we directly write the Boolean expression. And here we are writing the Boolean expression using the logic operator AND operator. And I have already explained you what are logic operators. In this case, to define the AND operation for this AND gate, we are using AND operator. It is performing AND operation between X and Y, the inputs, and storing the result inside the output signal Z. So, Z is assigned X and Y. So, this simple line is defining the AND operation for this AND gate. And after this AND operation, we can end this architecture using the keyword end and the name of the architecture data flow. So this is our VHDL code using the data flow architecture for this AND gate. Similarly, we can write the VHDL code for the XOR gate separately. Starting with IEEE library, then we have entity. And here I am naming this entity as XOR underscore gate because I am writing the code for the XOR gate. And here we have two input XOR gate. So we are defining two inputs, let's say P and Q, and one output R. And both of these inputs and output are of standard logic data type. After the entity, we can write the architecture. And here, again, I am writing this architecture and naming it as data flow. So, data flow architecture of XOR underscore gate is. Why data flow architecture? Because here I am writing the Boolean expression. Now, this Boolean expression includes XOR logical operator, which is performing the XOR operation between these two inputs P and Q and storing the result inside the output signal R. So, R is assigned P XOR Q. And after performing the XOR operation, we can end this architecture using the keyword end and the name of the architecture data flow. So this is our VHDL code for the XOR gate. So in this way we have written the VHDL code for the AND gate and the VHDL code for the XOR gate. And here we can see that the half adder is made using the AND gate and the XOR gate. So let's write the VHDL code for the half adder by connecting AND gate and XOR gate following structural modeling. So this is our structural modeling code starting with IEEE library and standard logic package. Then we have our entity, and here I am naming this entity as half underscore adder. Why half underscore adder? Because we are writing the structural modeling code for the half adder. And inside the entity, we will declare the input and output ports. Here, A and B are our inputs, and sum and carry are our outputs for the half adder. And both inputs and outputs are of standard logic data type. After port declaration, we can end this entity using the keyword end and the name of the entity half underscore adder. Now after entity, we will write the architecture for this structural modeling code. Now understanding the structural modeling architecture is very important. Now here starting the architecture with the keyword architecture, and I am naming this architecture as structural of entity half underscore adder. Now, inside the architecture, we will not write any Boolean expressions or if-else conditions like data flow modeling or behavioral modeling. Now, as the name suggests, structural modeling. So, inside the structural architecture, we will declare the components that we want to use to create our structure. For this half adder, what are the components? We have one XOR gate and one AND gate. So inside the architecture, we will declare XOR gate component and AND gate component using the keyword component with the same entity name of the components. Let's see. Here, we are declaring the two components XOR gate and AND gate using the keyword component XOR underscore gate. Now, the name of the component must be same as the entity name of the component XOR gate that we have written in the previous slide. Similarly, the name of the component AND underscore gate must be same as the entity name of the AND gate that we have written in the previous slide. Now, the keyword component tells Vivado that there exists a component named as XOR underscore gate. Now, inside the component, we will declare the input-output ports of the component that we want to use for the structure. So, for XOR gate component, here we are taking both the inputs P and Q and one output R. And both inputs and outputs are of standard logic data type. After port declaration inside the component, we can end this component using the keyword end component. Similarly, for the component AND underscore gate, we are taking the two inputs X, Y and one output Z. And both inputs and output are of standard logic data type. And after the port declaration, we can end this component using the keyword end component. Now, inside this architecture, we have declared one XOR gate component and one AND gate component because in half adder, we have one XOR gate and one AND gate. Now, imagine if we want to write the structural modeling code for the full adder, which includes two XOR gates, three AND gates, and two OR gates. So, do we need to declare two components for XOR gates, three components for AND gates, and two components for OR gates inside the architecture? No. We will use single component for XOR gate, single component for AND gate, and single component for OR gate inside the architecture, and we will use multiple copies of these logic gates using instances. Now, this is all about a full adder. Now, let's get back to the half adder. Now, in half adder, we have only one XOR gate and one AND gate. It means we need to create only one instance for the XOR gate and one instance for the AND gate, and then connect them together to create our half adder. Now, let's see how to do that. For that, in the same architecture, we will write our code starting with begin. Now here, U1 and U2 are the instance names. They are not any signals, variables or components. They are simply names that we are using for XOR gate and AND gate. And how to declare them? Just like we declare input and output ports. Here, the instance name U1 colon to declare it for XOR gate. Similarly, instance name U2 colon AND gate. Now, for the full adder, we need to declare two instances for the XOR gate, three instances for the AND gate, and two instances for the OR gate. Now, in the case of half adder, since we have only one XOR gate and one AND gate, so here we are declaring only one instance for the XOR gate and one instance for the AND gate. So I hope you understand what are instances. Overall, the instances are the copies of the components that we are using to create our structure. Now let's see what we have next. U1 as XOR gate, port map, inside the parenthesis A, B, sum. Now, the keyword port map will map or connect the input-output ports of the XOR gate PQR with the input-output ports A, B, sum of the half adder. Similarly, for U2, keyword port map will map the input-output ports of the AND gate XYZ with the input-output ports A, B, carry of the half adder. Now, let's visualize this to make it more clear. Here we have instance U1 for the XOR gate. Now, the keyword port map will connect the input ports PQ of the XOR gate with the input ports AB of the half adder and connects R, the output port of the XOR gate, with the output port sum of the half adder. Similarly, we have instance U2 for the AND gate, where port map will connect the input ports of the AND gate with the input ports AB of the half adder and output port Z of the AND gate with the second output carry of the half adder. So, I hope you understand these port map connections. Now, after port mapping, we can end this architecture using the keyword end and the name of architecture structural. So, this is the complete structural modeling code for the half adder. Now, let me quickly summarize what we have just discussed. Structural modeling describes how hardware components are connected. So, in structural modeling, we describe the internal circuit structure, where we see how the circuit is physically connected using components and their interconnections. So, structural modeling describes how hardware components are connected. Second point, structural modeling follows low level of abstraction. We have already studied what is a high level of abstraction and what is a low level of abstraction. Low level of abstraction is closer to the hardware, meaning here we describe how the hardware is built using components, logic gates and interconnections. It is similar to a circuit diagram. So, structural modeling follows low level of abstraction. Third point, structural modeling uses components and port mapping. Just like here, we saw that structural modeling includes component declaration using the keyword component, and then we use keyword port map to map these components. So, structural modeling uses components and port mapping. Last point, structural modeling is similar to circuit diagram. In structural modeling, we describe multiple components and then we connect them using interconnections. So, it looks like a circuit diagram. Therefore, structural modeling is similar to circuit diagram. So, I hope you understand these points. Now, let's see few advantages and disadvantages of structural modeling. Starting with advantages. The first advantage is clear hardware structure. Using structural modeling, we can clearly see each and every component and their interconnections. So, structural modeling make hardware clearly visible. Second advantage, large circuits are easier to design by dividing them into modules. Now, using structural modeling, we can create large circuits by breaking them into smaller modules or smaller components. Just like we saw, we created multiple components and then combined them together to create our larger circuit, which makes the overall process very easy. Third advantage, components can be reused in different designs. Now, using structural modeling, we can reuse the same component in multiple designs, which saves our time and energy. So, components can be reused in different designs. Next advantage, useful for designing complex and hierarchical digital systems. Now, using structural modeling, we can create complex circuits by breaking down them into smaller modules in step-by-step manner. First, we will create smaller components and then combine them to create a larger component, and then we can combine these larger components to create our complex circuit in a hierarchical manner. So, using structural modeling, we can create complex circuits and hierarchical digital systems in a very simple manner. So, these are the advantages of structural modeling. Now, let's see few disadvantages. The first disadvantage is requires more code compared to other modeling styles. Now, compared to other modeling styles like behavioral modeling or data flow modeling, in structural modeling, we created separate components and then we declared those components, and then we created multiple instances, and then we used port mapping to connect these components. So, in structural modeling, we require more code compared to other modeling styles. Second disadvantage, it is not suitable for designing very small circuits. Now, structural modeling is not suitable for designing smaller circuits because in smaller circuits, we don't have multiple repeating components. So, we don't need to create multiple instances and then connect them together to create our circuit. We can simply use data flow modeling or behavioral modeling to design smaller circuits. So, these are the disadvantages for structural modeling. And I hope you understand advantages and disadvantages of structural modeling. With that, we are done with this topic of structural modeling, and I hope you understand this. So, we are done with this lecture. I will see you in the next one. Thank you.